Hello, science fans! Today we are going to talk about something really cool. It's called a quantum computer. Now you probably use a computer every day. You use it for school, for games, or to watch videos. Those are called classic computers. They are super helpful, but they have limits. A quantum computer is a brand new kind of computer. It's not just a faster version of the computer on your desk. It's a completely different machine that works in a very strange and wonderful way. It follows the rules of the quantum world, tiny particles like atoms and electrons. This world is weird but incredibly powerful. Imagine a big library with millions of books. You're looking for one specific sentence. A classic computer would read every book one by one. That could take a very long time. A quantum computer can look through all the books at once. It's like millions of copies of you, each reading a different book. This power comes from quantum physics. These rules let quantum computers solve problems too big for classic computers. So, what makes them special? It's how they store and work with information. Your computer uses bits, like switches, on or off. Before we can understand the new, let's make sure we understand the old. Let's talk about the computer you use every day. We call it a classic computer. Every single thing your computer does is broken down into a very simple code, showing a picture playing a song. This code is made of only two things, the number 0, the number 1. Think of it like a light switch. Light switch off diagram labeled 0, light switch on diagram labeled 1. A light switch can only be in one of two positions, on or off. There is no in between, that's it. Every letter you type, every color on your screen is a long string of zeros and ones. Each 0 or 1 is called a bit. The word bit is short for binary digit. Binary just means there are only two options. Inside your computer are billions of tiny switches, transistors, that are on or off. When you save a file, when you click your mouse, the computer flips these tiny switches in a pattern. It's like sending a secret message using a flashlight in the dark. Flash on, flash off to create letters and words. Classic computers flip switches incredibly fast. Let's think about numbers. Now, let's leave the land of on and off and enter the quantum world. If a classic computer uses bits, a quantum computer uses something called a qubit. The QU part stands for quantum. A qubit is like a magical version of a bit. Remember how a bit is like a light switch, either on or off? Well, a qubit is different. It can be a 0, it can be a 1. But it can also be a 0 and a 1 at the exact same time. I know it sounds a little bit strange, but this is the first big cool idea in quantum computing. It's like having a dimmer switch instead of a regular light switch. This special ability of a qubit to be in multiple states at once is called superposition. Imagine you spin a coin. While it's spinning in the air before it lands, what is it? Is it heads or tails? In a way, it's both at the same time. It has a chance of being heads and a chance of being tails. A qubit in superposition is like that spinning coin. It's a mix of both 0 and 1. It's only when we look at it or measure it that it has to choose. When the coin lands, it's either heads or tails. When we measure a qubit, it will collapse and be either a 0 or a 1. But the magic doesn't stop there. Qubits have another superpower called entanglement. This is one of the weirdest and most amazing ideas in all of science. When two qubits are entangled, they become connected in a very special way. No matter how far apart they are, across the room or across the galaxy, they are linked. If you measure one qubit and find out it's a 0, you instantly know that its entangled partner will be a 1. It's like having a pair of magic coins. If you flip them and one lands on heads, you know for sure the other one will land on tails, even if it's miles away. This spooky connection, as one famous scientist called it, is a key part of what makes quantum computers so powerful. It allows qubits to work together as a team in a way that classic bits never could. Let's dive a little deeper into superposition because it's so important. Think of it like a guitar string. When you don't touch it, it's still. We call that 0. When you pluck it hard, it rings a high note. We call that 1. But pluck it gently. It vibrates with a mix of notes, harmonics. It's not a single pure note. It's a combination of many. A qubit in superposition is like that gentle pluck. It isn't just 0. It isn't just 1. It's a controlled mixture of both at the same time. Let's use another example. Imagine a maze. A classic computer explores one path at a time. It goes down a hallway, hits a dead end, turns back, tries another. It repeats until it finds the exit. This can take ages. A quantum computer can explore all paths at once, like sending ghost versions down every hallway simultaneously. The ghosts explore together and find the exit much faster. This both ability lets quantum machines handle massive info. 2 qubits don't give you 2 pieces. They let you work with 4 states at once. 3 qubits let you work with 8 states. Each added qubit doubles the states. Okay, let's talk about that other superpower, entanglement. It's a bit mind-bending, but it's also really cool. Imagine you have a pair of special gloves, a left one, a right one. You put them into two separate boxes and you mix them up so you don't know which is which. You keep one box and you mail the other box to a friend on the other side of the world. At that moment, you don't know what's in your box. It could be the left glove or the right glove. But the instant you open your box and see a right-handed glove, you know something with 100% certainty. Your friend's box must contain the left-handed glove. Entanglement is like that, but even stranger. When two qubits are entangled, their fates are linked. They are created as a pair, like the gloves. For example, we can entangle them so that if one is measured as a 0, the other will always be measured as a 1, and vice versa. Before you measure them, each qubit is in a superposition of both 0. So, we have these amazing qubits with their superpowers of superposition and entanglement, but how do we actually get them to do anything useful? How do we make them compute? In a classic computer we use something called logic gates. These are tiny circuits that take in bits and give out a new bit based on a rule. For example, an AND gate only outputs a 1 if both of its input bits are 1. These simple gates are the building blocks for all the complex operations your computer performs. Quantum computers also have gates, but they are called quantum gates. Quantum gates are the tools we use to control the qubits. They are the actions we perform to change a qubit's state. Instead of flipping a switch from on to off, a quantum gate can do something much more subtle. For example, one of the most basic quantum gates is called a Hadamard gate. A Hadamard gate is what we use to put a qubit into superposition. If you start with a qubit that is in the 0 state, and you apply a Hadamard gate, you transform it into a perfect 50-50 mix of 0 and 1. It's like taking a coin that is heads up and spinning it perfectly. Another important type of gate is one that creates entanglement. A CNOT gate, which stands for controlled knot, is a 2-qubit gate. It works like this. It looks at the first qubit, which we call the control qubit. You might be thinking, this all sounds very complicated. Why do we need to build these strange computers? Some problems are just too big for our best classic supercomputers. A classic computer solves problems one step at a time. For many tasks, that's fine. But imagine a problem with a huge number of possible answers. A classic computer has to check each one by one. If there are 1,000,000 possibilities, it checks 1,000,000 things. If there are 1,000,000,000,000,000 possibilities, it checks them all. The time it takes grows in a straight line with the number of possibilities. Quantum computers are different. Because of superposition and entanglement, they can look at all the possibilities at the same time. Let's go back to the library example. A classic computer is like one librarian checking every book page by page. A quantum computer is like a team of 1,000,000 librarians, all looking at different books and communicating instantly. What would take the single librarian years, the quantum team could solve in minutes. The power grows exponentially. Adding a qubit makes it a lot faster, not just a little. This exponential power is the key difference. Think about it this way, 4 bits represent one number between 0 and 15. 4 qubits represent all 16 numbers at once. Let's talk about one real-world problem that quantum computers could solve much faster than classic computers. This problem is very important for security on the internet. When you buy something online or log into your bank account, your information is protected using something called encryption. Encryption is like locking your information in a box with a secret key. Only someone with the right key can open the box and read the information. One common way to make keys is multiplying 2 very large prime numbers. Let's say you have 2 prime numbers like 13 and 17. A prime number is a number that can only be divided by 1 and itself. Multiplying them is easy. 13 times 17 equals 221. The number 221 is the public key. It can be shared with everyone. The 2 original numbers, 13 and 17, are the private key, which you must keep secret. Now, if I give you the number 221, so, where does all this lead? We've learned that quantum computers, powered by the strange rules of qubit superposition entanglement, can solve certain problems that are impossible for our best classic computers. They can do this by exploring a vast number of possibilities all at once. We are still in the very early days of this technology. Today's quantum computers are like the classic computers from the 1950s. They are big, expensive, and can only handle a small number of qubits. They are also very sensitive and need to be kept extremely cold and isolated from any outside noise. But scientists and engineers all over the world are working hard to build better and bigger quantum computers. As they improve, they could start to change our world in some amazing ways. One of the most exciting areas is in medicine and materials. Designing a new drug or a new material, like for a better battery, involves understanding how molecules behave. Molecules are quantum systems. Simulating them on a classic computer is very hard, but a quantum computer is a quantum system itself.